Yeah, so thank you. Can you hear me all right? Okay, so I'm afraid this talk is slightly too long because, anyway, let's not go there. So the main work done is, of course, by the people under my name, underneath my name, and all part of this Data Assimilation Research Center. So let's go ahead. So what's particle filtering? So the idea is I'll tell a bit about recent developments in particle filtering and present thinking, and then show you some examples. One example, a high-dimensional example. So the idea is we have a set of particles, a set of model states, which we call particles from now on, and they're fixed, right? In the sense, so we know what they are. These states are set, and what we want to do, we want to get close to these observations in the future, at the red crosses, and so we can do it in several ways. Of course, we use the model equations. These are typically stochastic equations, so there's some freedom there. And what we want to do is, so we want to move the, if you like, the probability mass distribution from the blue dots to close to the red dots, we want the particles to describe the posterior probability density at that time. Now, in particle filtering, you collect weights, and the weights are caused by two processes. One of them is how close you are to the observations. The other one is how close you stay to the deterministic model equations. And it's this balance of weights that determines the final weight of the particles. And clearly, what we have to the one thing that's important is we know we have exact expression for these weights, which we can just calculate them exactly. Now the thing is with particle filtering that the weights tend to vary widely, also widely perhaps, but widely. And so the goal that we have in particle filtering is two things actually. We want to get the particles close to the observations because that's where the high probability regions are in these high dimensional systems. So that's the high probability posterior PDF values are. But we also want them to have similar weights, because otherwise the whole thing is useless. So we really want to bring this probability from one place, from the blue dots to close to the red crosses. Okay, so the weight of the particles for each particle you can describe it as the target probability. So the posterior probability density of that particle given its starting point, divided by the actual route they took, or I should say the density from which I draw the particle, which is this q. So it's this p over q, that's the weight of the particle, and that's what we're going to concentrate on from now on. Because like I said, we want these weights to behave well, meaning being close to each other. Now typically we'd like to draw from a high-dimensional Gaussian. If we can do that, we know how to do that in high dimension. We know how to draw from a Gaussian, so we can rewrite the weights as in the second equations. Second equation, where is it? Oh no, what am I doing? That's not what I wanted to do. Almost there. Yeah. So in this equation, you see we've changed the argument here from x to xi. So xi is drawn from this high-dimensional uncorrelated Gaussian. And that, of course, gives rise to this Jacobian over here. But the essence is that we can write the weights in this form, this equation down here, in which f is related to the posterior density. And so we can write the posterior density always as the exponents of something, exponent of minus f. So that's what we've done here. So the f is from the posterior PDF, and these two terms are from the proposal density. So one is the Gaussian term, and the other one is from the Jacobian. And A is a matrix to ensure that we do the dimensions right. So the different particle filters differ in how they use this equation, and that works as follows. So if you look at the implicit particle filter, just briefly, again, this is expression for the weights. That's the first equation. And then the idea is that we solve x, so we have an implicit equation for x. And that's the second equation over there. We just solve it that way. And which means that we draw from the Gaussian, so we know what xi is, and then we solve this equation, because we also know what f is. That's the expression comes from the posterior PDF. You know exactly what it is. We can just, now there's an infinite number of solutions, and we just choose one, typically with a random map. I don't want to talk about that. But you see is that the weights end up to being the minimum of this f plus this Jacobian term. It turns out for high dimensional systems with a lot of observation that these weights are still vary too much. And yeah, so we have to do something better. Now, the other thing we can do is another method is the so-called targeted implicit particle filtering. Again, we have the expression for the weights over there, and this time we try to find the position of the particles or the trajectory of the particles over time by solving the second equation over here. So you see we do something different. We make the whole argument of the weight equal to a constant that we choose. And so what we do is we choose a value for j. So on the right hand side, what you see there is the minimum of f. Trying to get more, yeah, here we are. The minimum of f, but then taken taken as that minimum for one of the particles, and we choose that particle. So it can be the minimum, the lowest minimum of all the particles, can be the highest minimum for all the particles. We can choose whatever we like. So it gives rise to a certain percentage of particles that can actually reach that weight, and the others come in through resampling. It's a bit more, well, there's a bit more to say about that, but it just isn't time. If you're interested, we can talk about it later. Anyway, when you do this, then you get that the weights are proportional to the exponent of minus this constant that we've chosen. So by construction, all the weights are the same. And so that's nice, of course. So we have achieved that goal, but the problem is, of course, that we have a tuning parameter. How to choose this j? Which value should we choose? Or should we actually choose at the minimum of f, or should we do something else? There's more freedom. And finally, I didn't have a name yet, which I call new implicit particle filter, if you like. Again, we have expression for the weights, and now we solve x from putting this Jacobian term equal to the minimum of f, and again gives rise to a different set of weights. And it turns out that these weights the weights can be shown to be quite similar. So that's another way of generating particle filters. So you see, there's an enormous amount of, suddenly I hear myself. There's an enormous amount of methods you can use to come up with particle filters. Let's do a very simple model. So it could be a very high dimensional model. We have an independent set of variables at time 0, so the upper index there of x is time. We take one time step of this model, and the model is very simple. It's just an identity plus some random noise with the distribution that's given over there, the Gaussian distributed noise, and it's again uncorrelated. And then we take observations at time 1, and your observations, of course, have errors, and also these errors are uncorrelated. And we're going to do a particle filter on this system with only 10 particles. We're going to crank up the resolution and just see what happens for the different methods. So this picture shows you the root mean square, and these are averages over typically about 100 realizations, because there are all random numbers involved, 100 realizations, just to make sure we get rid of the statistical noise. So we have the root mean square errors. Of course, in this case, we know the exact solution against the dimension of the system, running from 1 to 10,000 for all the different particle filters. So we have the standard particle filter, something I call the equivalent weights particle filter, the EWPF, which is very close to the target implicit particle filter I just mentioned. We have the implicit particle filter, or the optimal proposal density. They're the same in this case. Also Metropolis-Hastings, preconditioned Crank-Nicholson, and Mala has a few other methods in there. So what you want, the true root mean square error we know, of course, in this system, because it's all linear. It's about 0.37, and you see the red line, which is the equivalent weight particle filter, is very, very close to that, irrespective of the dimension of the system, right? It just works pretty nicely. The other ones have more difficulty, as you see. And 1, the root mean square error is 1 is sort of the limiting value, because that's more or less what the prior would give you. Okay, I can also look at the effective ensemble size. So how many particles do I actually have in my ensemble? I start out with 10, but because of all this weighting process, of course, I lose particles. If the weight gets too low, effectively, that particle is useless. So I have here effective ensemble size from 0 to 9, again, against a system dimension. And we see that for different particle filters, well, we get all these different results. Important is, again, that the equivalent weights particle filters up there is in red, keeping the 90%, keeping 9 out of 10 particles. That's a set number, like I said, the tuning parameter. But we see also that the new particle filter has pretty good behavior. Even if the system dimension is cranked up drastically, we still see, well, actually, we see increasing in performance, which the theory also suggests. So, message here is, for this very simple system, we have particle filters that work in very high dimensions. Right? There are no issues there. And I have 2 minutes to talk a bit about the climate model implementation. So what I'm showing here is for the equivalent weights particle filter. So the particle filter in which I set all the weights equal to a certain number. And in this case, I make it the lowest number that, the lowest minimum. So all the particles are kept in the system. Well, you can, what I've been explaining this, you could have read all this stuff. It's about 2 million variables, and well, it's a simple climate model, relatively simple. Ocean, there's an ocean in the atmosphere, and that's more or less it. We use the Empire data simulation framework, but I won't talk about that. We observed sea surface temperature daily. Why sea surface temperature? Well, it couples ocean and atmosphere, so it seems to be a good variable to start with. Well, that's more like this. So some results, you can't really see that, but there's, okay, so on the left-hand side, we have the root mean square error here. The green line, which is a line up here, is what a free model run would do. So a free ensemble, a forecast, just a forecast ensemble would do. That is the error there. And when doing the data simulation with different tuning parameters, like I said, there are different tuning parameters in the system, you get different results. Which of course is confusing. And the difficult part in this, we do have a particle filter that doesn't blow up, but the results depend on the tuning parameters, and perhaps too strongly. So what we're doing here is not robust. And this is the observed variable on the left-hand side, on the right-hand side we have an unobserved variable. And it's interesting to note that the green line is up somewhere here, so we don't do much with the data simulation. But, I mean, for some tuning parameter combinations, we do get results that are worse than doing no data simulation. And we do understand why that is. But it's just purely related to the fact that we only observed a tiny fraction of the whole system. Okay, so you can also, of course, look at how the ensemble is behaving over time. So on the horizontal axis we have time. Red is the truth. Yellow is the forecast ensemble, and blue is the analysis ensemble. Okay, we can look at rank histograms. You want the rank histogram to be flat. Well, they're almost flat, but not exactly. So the ensemble is slightly undispersive. We can try to say something about the estimated PDFs. There's no time to go into that. The only thing I forgot to say is we use 32 particles in this system. Anyway, to conclude, not only the particles should be close to the observation, but also the weights need special attention. We really have to think about moving probability densities around. We do have particles for high-dimensional systems, but we need to make them more robust. And, well, that's more or less the whole thing. Thank you.
So we have time for one question. Yes?
So that last point over there, so the difference is you have like PDFs in 3D space, so from every pixel you have a PDF. How do you represent the PDF from every point in space?
So, well, I have a number of particles, and the particle have of course, a value in every point in space. So,
how do you visualize it?
Oh, well, that's a different session, I guess. No, these are of course, well, there are all kinds of issues. It's over. So the biggest problem I want to emphasize here is that we can afford, let's say, 32 particles. So we have 32 model states to represent posterior PDF in a 2 million dimensional space. what exactly do we want from these particle filters? That's well, the question I raised there. Yeah, that's even apart from the visualization.
Thank you. Sorry, we have to
Yeah.
move on.